Alright, so today we're going over maximum and minimum values. So essentially this topic is a visual accumulation of derivatives and the graphs in specific. So you really want to learn here how to visualize a graph and tell what's happening within a graph, whether it's the derivative graph, the first derivative or the second derivative, as those are the most common types of graph you will see. So let's go over some basic main really values here. So let's say you have function f of x. Let's actually give it an equation. Let's say it's x cubed plus 4x squared plus 3. And so the zeros of f of x will give me the position changes, which is depicted by this graph right here. The zeros will be obviously when it touches the x-axis, and this is essentially just meaning that the position is going from negative to positive. And now we're going to go on to the minimum and the maximum. So on a function graph, when you see the minimum and maximum points of the graph, it's essentially noting that the graph is changing direction, or rather the derivative. It's also the zeros of the derivative function. So essentially, it's the velocity. For example, if it's from a position going from a negative to a positive or a positive to negative. And now the final one, which is concavity. So concavity is basically, if we look at a first derivative, or rather just a function of x, concavity is kind of just, if you think about it, it's the direction in which the graph is going towards. So if we look between the interval between these two circles, we see the graph is concaving down, and then outside the interval, we could kind of see it's concaving up as it's creating sort of like a U shape. And the concavity of f of x would be depicted by the minimum and maximum values of the first derivative graph, and also the zeros of the second derivative function, or also the graph. All of these three would depict that concavity changes. So if you're always unsure about concavity or zeros, whether a graph is changing direction or not, you could always just find derivative and then find the zeros or minimum maximum and work your way from there. Alright, so let's start off with number 3. So one thing we haven't gone over yet is absolute maximum and absolute minimum. So some rules with absolute maximum and minimum, it is exactly what it sounds like. It's the highest most point in a graph and the lowest most point in a graph during an interval. But one main thing to note is that the endpoints right here, like the end of the interval, they could be absolute minimum and maximums, but they can never count towards local minimum or maximum. So for example, S here would be absolute maximum, and A over here, if the interval were to continue, it could be a local maximum. But by the rules of calculus, it cannot be absolute maximum or a local maximum. So let's start on with the question. So we got to identify all of the letters and state whether they're max, minimum, and then or neither. So let's write down the letters here. We got A, B, C, D, R, and S. So A, we already talked about that. That's neither. So we're just going to write neither. And then B is going to be a local maximum because it's not the lowest point in the graph, but is one of the low points in the graph. One way to note or see if it's a maximum or minimum is to see how the concavity changes throughout the graph. So B, we are going to write local minimum. And you could also write the y value, which, we actually don't know the y value here, but usually if the graph is scaled or numbered, you could write down the y value. But C is going to be a local maximum. And then D is going to be neither because it's in the middle of a concavity change, and to the left of it, the graph is going up, and to the right of it, the graph is going down, so it's neither again. And then R is going to be absolute maximum, or absolute minimum rather. And then S, as we talked about, since it's at the end of the interval, it could still be denoted as absolute maximum. Absolute maximum. All right, so let's move on to these few questions here. So for these 5 questions here, we want to find out the critical numbers. So the critical numbers are essentially when the minimum and maximum values of the graph. And as we talked about before, when a graph reaches a minimum and maximum value, the derivative becomes 0, or the tangent line becomes horizontal. So what we want to do here is find the derivative and then solve for x. So let's start off with number 29. Number 29 is function f of x is equal to 3x squared plus x minus 2. And now we need to find the derivative of it. So we could just use the power rule, which would be 6x plus 1. And now all we need to do is set it equal to 0 and figure out what the x value is, or rather, which would be the critical value. So we could move over to 1 to the other side. So we would have 6x minus negative 1 or equals negative 1, divide by 6, and we would be left with x is equal to negative 1 over 6. So essentially the critical value here is at x equals negative 1 over 6. And if you need to find the y value of the critical value, all you need to do is take this and then plug it into the original equation, and that would give you the coordinates. But of course here we do not need to do that. Alright, so let's take a look at number 30. Number 30 is v cubed minus 12v plus 4. So again, we're going to use find the derivative using the power rule. So we're going to have 3v squared minus 12v, or minus 12. And now what we're going to do is set it equal to 0. So we can move over to the 12 to the other side. So we're going to have 3v squared equals 12. And we could divide by 3 on both sides. We're going to have v squared equals 4. And then square root it. So we're going to have v is equal to plus or minus 2. And that would be the x values, or the v values rather, where which this function has a critical point at. So another way to tell how many critical points you should have is if you look at the highest exponent in the function. Usually for functions, your number critical value should be 1 less than the exponent. So for this one, the magnitude power of the function is 2. So we have 1 critical value. Because the graph would look something like this. So we would only have 1 point at which there's a horizontal tangent line. And for number 30, we have a power of 3, so we're going to have 2 critical points, negative 2 and 2. So let's move on to number 30. Number 30 is going to be 3x to 4th power plus 8x3 minus 48x squared. So we're going to use a power rule again, so we're going to have 12x3 plus 24x2, and then that's going to be subtracted by 96x. I believe 96, right? Yeah. And now what we're going to do again is set it equal to 0, or rather, factor it out. So we're going to have, we could factor out x, and we could factor out, I believe, 12x. I have 12x, x squared plus 2x minus, that's going to be 8, I believe. Yeah, 8. And now we could just factor out this inside, which is going to be x plus 4, and then that's going to be minus 2, and 12x. So we could deduct that the x values here that would equate to an answer of 0 would be x equals 0 right here. So our critical points will be at x equals 0, negative 4, and 2. And those are our critical numbers right here. Alright, so I want you guys to try number 5 and number 6. So essentially for these, just indicate all the local maximum and minimum values, as well as the absolute maximum and minimum values. So you can pause the video and try that out. Alright, so let's take a look at number 5, the graph. So first let's take a look at the absolute values, or absolute maxes. So we see there's a maximum at here, which is going to be 2, 3, 4. So it's going to be f of 4. So f of 4 is going to be our first or and only absolute maximum. Now let's take a local maximums. So for local maximums, we're also going to have f of 4 and f of 6. So the reason why they're both local maximum and minimums because they're inside the interval, but if the maximum would be outside or at the edge of the interval rather, it cannot register as a local maximum as well. So for local maximums, we're going to have f4 and f6. And now for local minimums, also I haven't talked about this, but you would think that f of 1 would be a local maximum, but here you could see the defined point is actually under the limit of the actual graph as it reaches 1, so it wouldn't register as a local maximum. Even though the concavity is down at that point, but it doesn't matter. So let's check out local minimums now. So our first local minimum is going to be at f of 2, which is right here is a horizontal tangent. And then, so we write down f of 2. And then our other local minimum is going to be f of 5. So at x equals 5, because there's a, downward jump there, so we're going to have f of 5. And then our final minimum value is actually going to be f of 1. So we're going to put f of 1 right there. It's very sloppy. But the reason why that's a minimum value is because the defined value is below the limit of the graph. So it does get confusing at times, but if you know what you're to expect and what you're looking for, it kind of eliminates all the misconceptions that there is. So let's take a look at number 6 now. Number 6, let's write down the absolute max. So the absolute maximum value here is going to be, it would be over here, but since that point is not defined, even though it's at the edge of the graph, it's not defined, so the absolute max would be just nothing. So we could just put no answer. And same thing for number 5 as well. The absolute minimum would be this point right here, but it's not defined, even though it could be a limit that exists. So that's why the absolute minimum did not exist in number 5. And the opposite is the case in number 6. So let's take a local maximums. So local maximums must be within the interval. So for the first one, we have f of 3 and then f of 6. So we could write f of 3 and f of 6. At f of 3, it reaches a y value of 4, and then f of 6, it reaches a y value of 3. And let's take a look at local minimums. So our first local minimum here would be f of 2, because the y value is at 2, even though the limit limit exists, but the point is undefined at the limit. The defined point is below the limit, so it still counts as a local minimum. So we have a local minimum of f of 2 and we have another one at f of 4. And we also have technically a minimum here. If it was the lowest most point, it would register as an absolute minimum, but here, since it's at the edge of the graph, it's not an absolute minimum. It would not register as a local minimum because it's not in the realms of the interval. Alright, so I want you guys to try out number 7, 8, 9, and 10. So I've kind of pre-written the graphs here, but essentially you want to take the information they give you and sketch a graph of what you think it should look like and what based on the conditions. So you could pause the video and try this out. Alright, so let's take a look at number 7. Number 7, we have our first condition of absolute max at 5, and then absolute minimum at 2, and then a local max at 3, and then local minimum at 2 and 4. So first, what we should do is just plot points that describe those conditions, and then we can just connect them through a correct concaving graph. So we have an absolute minimum at 5. X equals 5 would be right here. Let's put the maximum right here. And then we have a minimum at x equals 2, so we could put the absolute minimum right here. And then we have a local maximum at 3, so 3 is going to be right here. So let's put the maximum right there. And then we have a minimum at 2 and 4, so we're going to have a local minimum there and a local minimum right there. So now all we need to do is connect it, so we know the minimum's at 2. So what we could do is rather, that's going to be the absolute minimum. The graph goes up and then it goes back down at x equals 2 to describe a minimum. And then it goes up for a local maximum at x equals 3. And then it concaves down for another local maximum at x equals 4. And then it goes back up for its absolute maximum at x equals 5. That's a little bit dirty of a graph, but obviously you would want to draw it with a little bit more curvature, but just because of the space it was a little bit difficult. But you will see in future sections you want to draw it with a little bit of curvature because the pointy like maximums and minimums and the curved maximum and minimums make a difference in most notably the mean value theorem. So now let's take a look at number 8. Number 8, we have an absolute maximum 8 at 4, and then minimum at 5, and then a max at 2, and a min at 3. So let's draw the maximum here. So our 5, x equals 5 is going to be over here. So our maximum is going to be right up there. Minimum at 5 is going to be down there. Local maximum at 2, that's going to be right here. And then a local minimum at 3, that's going to be right here. So let's draw the graph out now. So we need to start the graph from the left side at x equals less than 2. Because if we started at 2, then we can't count x equals 2 as a local maximum anymore. Because it wouldn't be within the realms of the interval. So let's draw it out now. And it goes back down for x equals 3. That would be your local maximum. It goes back up for x equals 4. That would be absolute maximum. And then we can end it at x equals 5, which would be your absolute minimum. And since it's an absolute minimum, it doesn't have to be within the realms of the interval, but it can be on it. So that would be your final graph there. Now, number 9 is asking for an absolute minimum at 3, a maximum at 4, and a local maximum at 2. So let's draw that out. So our x equals 4 is going to be right here. So our minimum is going to be down here. Maximum is going to be up here. And then our local maximum is going to be right here. So we could just draw that out in a simplistic way. So we have concave up and then a concave down, maximum, absolute minimum, and then a local maximum. And that would be your final graph for that. The number 10 is absolute maximum at 2, absolute minimum at 5. And then 4 is a critical number, but there's no local maximum or minimum there. So what we could do is we could draw the graph in a fashion that the limit of the graph is reaching a horizontal tangent line, but the point at, for example, x equals 4 is not actually defined. So we can't depict a local maximum or minimum at that point. So if we, let's write out the graph here. So absolute maximum at 2, we're going to have our 5 right here. Absolute maximum at 2, where it's going to be right here. Minimum at 5 is going to be down there. And then 4 is going to be a critical number. So that's going to be a hollow circle. We could put that right there. These, for example, would be shaded in circles, just so you could tell the difference. So absolute maximum at 2, and then we could just make it go like that. And then down here for the absolute minimum at 5. So what this is kind of supposed to look like is an absolute maximum at x equals 2, and then the graph kind of goes down like at a really slow concavity, and it flattens out at x equals 4 to create a horizontal tangent, and then it goes down to x equals 5, which would be your absolute minimum. Alright, so I want you guys to try number 15 to number 21. So essentially for these, you're just going to be finding the critical values, which is also called local and minimum, maximum values, and also the absolute maximum and minimum values. So what does help is you could draw a graph for some of them, so you could kind of visualize it. But yeah, you could pause the video and try those out. Alright, so let's take a look at number 15. Number 15 is 3 minus 2x. So this is a function to the first power. So it's a linear function. So with the thing with linear functions is that you're not going to necessarily have local minimum and maximum values. It's just going to be an absolute max and absolute minimum, whether to the left or right of the interval. So for 3 minus 2x, we don't necessarily have to find derivative. We know the slope is negative 2x. So the graph would look something like this. And we have to depict it from the interval from -1 to infinity. So we could say the absolute maximum is at -1, which if we plug in x for -1, it would just be f of -1, which is equal to 6. That would be your absolute maximum. And your absolute minimum would just be, since this is the interval goes to infinity and the linear function goes down to infinity, negative infinity rather, you could kind of say that the absolute minimum is going to be negative infinity, but since the interval is not exactly specified, you would have to conclude that. And now let's look at number 16. So number 16 is x squared, and we're depicting it from the interval of -1 to 2. And now, so what we could do is just find the derivative. It's going to be 2x, and we could set that equal to 0. So 2x equals 0. You could divide by 2 both sides. It would give you x is equal to 0. So that is our only critical value. And x squared function that's positive would be concave up. So you could just conclude that the graph has an absolute minimum at x equals 0 or f0, and the absolute maximums would be at x equals -1 and 2, since those are the edges of the interval. And for the absolute maximum, you could depict that it happens at x equals 2 because it's within that interval. And then the local maximum would be at -1, since the interval also includes -1 here, so less than or equal to -1. We could say that the local max happens at -1. And now number 17 is function f of x is equal to 1 over x. And we could find derivative here. Derivative would just be a -1 over x squared, but we could also visualize it. So we know as the denominator goes to, since the interval is from 1 to infinity, or 1 to continuing on, we know as the denominator gets bigger, the number gets closer to 0, which means that the number would indefinitely be reaching a minimum. It wouldn't be going towards a maximum. So we could deduct that at f function 1, there is an absolute maximum, which at x equals 1, your y value would just be 1 because 1 over 1 is 1. And now let's move on to number 18. Number 18 is the same exact thing here. So I could also draw the graph out just to kind of visualize it here, so that it would look something like this. And then we also have this sort of thing going on this interval on the negative side, but we don't really need to focus on that side. So our interval is from 1 to 3. So same thing as the previous question, we could deduct that the absolute max of this is going to be at f1. And then since the number gets closer to 0, so it decreases as the x value goes to negative or infinity, we could deduct that the absolute minimum is going to be at f3. So for number 19 through 21, we're dealing with the same function sine of x. So what I've done is I've drew the derivative graph of sine of x, which is cosine of x right here, and then the sine of x graph is right here. So this is kind of to visualize the horizontal tangent in conjunction with the zeros of the derivative. So you could kind of see the horizontal tangents appear at pi over 2 and then 3 pi over 2. And you could kind of see on the derivative graph, the zeros of the function is at pi over 2 and then 3 pi over 2. So let's get started on number 19. So number 19 is sine of x from the interval of 0 to pi over 2. So 0 is over here, pi over 2 is right here. And this is greater than or equal to 0, but there's no greater than or equal to sign between pi over 2 and x. So we can deduct that there's an absolute minimum, at f0. But since it's not greater than or equal to at pi over 2, we can't really say that that's the absolute maximum. For visualization terms, it would kind of be like a hollow circle. We can't exactly say it's absolute maximum, even though the limit, although would exist there. And now number 20, it looks like it exacts the same question, but except the greater than or equal to sign is switched around. So for this, the absolute maximum would be at f pi over 2. And then here, the absolute minimum wouldn't exist because the greater than or equal to sign does not exist there. Now number 21 is sine of x from the interval of negative pi over 2 to pi over 2. So negative pi over 2 is going to be right here to pi over 2. And there's both greater than or equal to signs there. So we could say this is the absolute minimum and that's the absolute maximum. So the absolute min is going to be at f negative pi over 2. It's a little bit messy here. But and then the absolute maximum is going to be at f pi over 2. And those would be your final answers for all these questions. Alright, so that's basically it for maximum and minimum values. So this section is just being able to visualize what's going on in the graph, how concavity changes, the zeros of the function, minimum and maximum, and basically look at an equation and being able to kind of visualize the graph of it that you would use for your benefit maybe in a question. And there are a lot of rules to finding out the maximum minimums and the absolute maximums as well. These are some special kind of visualization techniques here that you could kind of memorize. And yeah, these would really help you answer questions and be able to figure out basically a maximum and minimums. So that's basically it.